Welcome back, marvelous AP Calculus BC students. We are moving on to some more advanced area of polar graphs. Last class you practiced area of some common polar graphs, but you only did the area of a single graph. Today we're going to look at the somewhat obvious extension of how do we find the area between two graphs. You might remember back to our rectangular graphs, right, where we had one function that was doing its own thing up here. Maybe we had another function that was doing something down here. And we said if we wanted to find the area between these two graphs, we would just take the top function, the area of the top function, and we would subtract that from the area of the bottom function. Visually, and that was probably a poor job on my part, visually what you would do is you would really find the area underneath the black function, which is this guy right here, and maybe if the black function was f of x, we'd say we found the area underneath f of x, and then you would subtract off the excess area, which is the area underneath the yellow function, this guy right here, and that's shown by the area from a to b. We'll call you g of x. And that would, of course, leave us with the area we are interested in, this guy up here. Well, good news for you. Polar graphs are extremely similar, except instead of going up and down like we did here, we draw our polar graphs from the origin, but still similar idea. There are a few little idiosyncrasies here, but overall, nothing too terrible. So, looking through, if we were interested in finding this green area that's right over here, we do the same thing. We find the area of the red graph, which I called g of theta, and the red graph would be drawn from in here. Then we find the area of the blue graph, which is also drawn from the origin up here, and then we subtract the two, which just leaves the green area. We looked at that last class and we saw it's 1/2 the function squared d theta minus, and then our new equation is 1/2 the other function squared d theta. Really nothing bad. Sometimes you will see it written separately. I somewhat prefer it like this so you can visualize the two graphs that are going on, but of course for the sake of efficiency these are often combined, the 1/2 factored out, and this is written as g of theta squared minus f of theta squared. Please make sure you do not call this, now we'll use parentheses, please make sure you do not call this g of theta minus f of theta squared, right? That is incorrect. We're not allowed to undistribute a square with subtraction or addition. So don't do that. Maybe even forget I even mentioned it. All right, example. Sketch the following graphs, then set up an integral to find the area inside the graph of one and outside of another. All right, our first graph is not bad at all. Sine of theta, it's along the y-axis. 3 sine of theta is just a circle with a diameter of 1, 2, 3. It's going to look something like that. Ew, I didn't like that at all. Something like that? Yeah, better. Sounds good. Circles are always tough for me. I have had those magic professors in college that could always do perfect circles, and I cannot. Oh well. The second function is a little trickier. 2 minus sine of theta. It's one that I probably wouldn't expect you to know how to do. However, you might notice the difference in coefficients here, and you might start to examine this graph, and you could say, well, the biggest sign can never be as 1. 2 minus 1 is positive 1, and that occurs when theta is pi over 2. So my guess is at pi over 2, that's the biggest the graph ever gets, a radius of 1. And then the smallest sign ever gets is negative 1. That occurs at 3 pi over 2. 2 plus 1 is 1, 2, 3. Then you also might notice the mismatch of the coefficients, right? In that this one is smaller than this, which means that this guy will never become, or I guess overall, this will never become 0, right? We're never going to get 2 minus 2, so we never get to the origin. And you also might realize that this is going to be a cardioid with no inner loop. Looks something like this, kind of flattens out like so. And the nice part is it doesn't have to be perfect. You could have graphed this incredibly wrong and still gotten the correct answer. So what are we trying to do? We want to set up the integral expression to find the area outside the graph of R1 To find the area inside the graph of R1. Ooh, that was tough for me. So this purple one, by the way, is R1, and outside the graph of R2. So this is all the area inside the graph of R2, which means this is the area outside of the graph of R2. Well, technically it's all of this outside, but they said that it also had to be inside the graph of R1. So inside the graph of R1 is all of this, but we're looking for just this piece right up here. How do we do that? Well, the first thing we should probably determine is where are we going to be drawing radii from? Okay, so what happens is as we draw a radius out this way, there are actually 2 points that are drawn, one here and one here. All right, nothing too crazy there. Then as we draw another radius out here, we actually have 2 points as well. That's not going to help us. Then as we draw a radius out here, now we have found where the two graphs intersect. And any radius, I think, after that, take a look at this piece up here, is going to give us a point here and another point up here, and we're interested in this piece in between. So I think our process for this problem is first we need to determine where these two polar graphs intersect, and then we're just going to need to draw a whole bunch of radii in between those two intersection points, and by doing that I think we'll have covered all of the area that we're interested in. Alright, so how do we do that? Well, if we want to find where these two intersect, we probably need to set the two equations equal to each other. So 3 sine of theta, where is that radius, equal to 2 minus 1 sine of theta. I think we'll need to probably add our 1 sine of theta to the other side. We'll switch to all one color for this. So we get 4 sine of theta, right? One of those plus 3 more is 4 equals 2. Dividing by 4, sine of theta equals 1/2. We've been doing enough trig at this point that hopefully you remember sine becomes 1/2 at pi over 6 and 5 pi over 6, right? I think that makes sense probably based on our graphs too. Okay, so we have pi over 6 and 5 pi over 6. Nice. Now, let's look at what happens if we treat each of these integrals separately. So for example, let's see what happens if we find just the area of R1 on that interval. So if I wanted to find the area of R1 from pi over 6 to 5 pi over 6, that was interesting. We would do 1/2, and then our function for R1 is 3 sine of theta squared d theta. Visually, what is that? Well, I'm actually going to erase all this so we can get a better idea of visually what's happening here. That would be, and I'm going to do my best to kind of shade all of this in here, that would be all of this, certainly including this part down here that we don't want, but that would find everything because it's between those 2 points. Alright, but then what if we looked at our other piece, and I said switch to green, and OneNote didn't listen to me, and we'd go from pi over 6 to 5 pi over 6. Oh, I did that again. Huh, must be a thing. 1/2, and then this one is 2 minus sine of theta squared d theta. Okay, well, if we look at that, that's going again between, should be between these intersection points, but apparently my drawing skills are not on par. And it's just going to be below, right? It's always going to be within that border. And of course, that's much too small. However, that's the overlapping piece, and so to find the actual value, we subtract the two. They did tell us to not evaluate. I think you'd have quite some trouble evaluating this. And that's about all there is to it. Now, it would be great if polar graphs were this easy, and sometimes they are. Honestly, we're kind of coming to the end where it's just like, here's a lot of extra information, but you already know how to apply it all. But there is one weird thing that can happen with polar graphs. So here we go. Life gets weird when you're trying to find overlapping area that's common to both, right? So we're going to look at the common area between r equals 3, and hopefully you can see that's a circle centered at 0, and r equals 6 sine of theta, 6 sine of theta, and this should be r equals 3, not r sub 3. There we go. And we're going to try to find the common area here. Well, let's kind of maybe approach it the same way we did last time. So let's maybe discuss why what we do last time would be incorrect. But we'll go through the same process. It could be important. So 6 sine of theta, we're going to set that equal to 3. Solution-wise, sine of theta equals 1/2. We've been here before. Theta equals, probably should be working sideways, but that's okay, pi over 6 and 5 pi over 6. We have these same subdivisions. Very nice. And I'll call them the same as before, pi over 6 and 5 pi over 6. Nice. All right, and then let's say we set up these two integrals again. So we want to find this guy in here. So you're probably thinking, oh, it's just going to be blue minus yellow. So let's find the area of the blue first. That'd be from pi over 6 to 5 pi over 6 of 1/2 6 sine of theta squared d theta. And then it seems like we should just be able to subtract the orange or the yellow one, whatever color this is. Same idea, pi over 6 to 5 pi over 6, 1/2. And then this one was just 3 squared d theta. All right, well, is that our answer? Maybe visually, let's see what we're doing here. So the blue area from 5 pi over 6 to pi over 6 would be, I'm going to retrace this in here, would be kind of this shape all the way around, kind of like a weird balloon slash alien head. I don't know. It'd be all of this. We're saying take all of that, and then if there's a subtraction sign here, just take away, and this guy is just going to be this sector of a circle. I should probably do this another way. So let's maybe go this way. This would take away this sector of this circle right here. And if you take the blue and take away the sector of the circle, I'm going to outline this in red, this is only going to leave this outer piece up here. And that's not what we're trying to find. They said the overlapping piece, not the piece that I just did in red. So this doesn't work. Drat. Going back through, we should probably find a method that does work. And I think the way that this does work is understanding how to subdivide this graph. Now, this work apparently was supposed to go down here, so if you want, you can, but you might just want to take notes on this part down below. So we have this guy here and this one here. And realize that we actually have 3 different segments of the graph going on. We do have the segment between pi over 6 and 5 pi over 6. In fact, that one's really easy to find. There's a couple ways I can think to do it, but I think this segment that's in the middle, which I'll do in purple right here, isn't this segment just the area between the yellow graph and the origin? In fact, couldn't we just draw radii straight from the origin out to the yellow graph? I think we could actually just find the area of the yellow equation from pi over 6 to 5 pi over 6, and it would find us that sector. Really, if you're being bold, you could just use your formula for area of a circle and then find that sector. But we don't need to go that far. So I think for this first part, and I'm going to go ahead and probably redraw these 3 pieces. So we had one piece that looked like that. Oh, that was pretty good. I'm pretty proud of myself. And we know that this rotation was pi over 6 and this one was 5 pi over 6. Okay. And then we have 2 little slivers that are left. So let's look at these slivers down here. And let's think about what functions are involved with this sliver. Well, we don't if I wanted to think about maybe just a line. That's a bad color. Let's use, no, green's not to have it red. Sure. If we think about a line that went out from the origin, we don't want to do yellow minus blue because that would actually give us this piece. In fact, I think if we draw a few lines from the origin, we only hit one function. We just hit the blue function here. And so if we're going to be talking about those slivers, I think the only graph that matters is the blue graph from where? Well, we start hitting it at 0, and we stop hitting it at pi over 6, I think. Once we go past pi over 6, then we hit the yellow graph first. So for these slivers here, right, we have one sliver, and I'll kind of draw them like this. So here is your pi over 6, and then we had this little guy that comes out, right? That sliver actually starts at 0. It goes from 0 to pi over 6. And then you had the other one that's on this other side, right? And it looks something like this. This guy over here. And this one also only has to do with the blue function. But now, if you're thinking in terms of rotation, 0, pi over 6, pi over 2, 5 pi over 6. Oh, we're back to pi over there, right? So this actually goes from 5 pi over 6 over to pi. Now, if that seems a little complicated to you, it might help just to think about how this blue circle is created, or maybe when the blue circle touches the origin. That could be a way to think about it too, where you could say, oh, let's take the equation for the blue circle and set it equal to 0. Sine of theta equals 0, which means that theta in this case is going to be 0, pi, 2 pi, so on and so forth. So our blue circle starts at a rotation of 0, that's here, gets all the way around to pi, and then we're good. And now, from pi to 2 pi, we do it again, and again, and again. Well, how does that help us? I think we can actually find the area of all three of these fairly easily. This purple one, we said was just this area here. It only involves my r equals 3 graph. So the purple one is just 1/2 r equals 3 squared d theta. And it's between pi over 6 and 5 pi over 6. That'll find the pi slice up above. But then I think we need to add on 2 more, and we'll just go in the order they're written. We need to add on the pi slice that goes from 5 pi over 6, kind of weird we're swapping the order here, to pi. And which function was in charge of that sliver? Oh, yeah, the blue function, so 6 sine of theta, right? So 6 sine theta squared d theta, and then we have one more sliver to add on, which is from 0 to pi over 6, 1/2 6 sine theta squared d theta. Great. That would absolutely find the area of the overlapping shaded area, and it's fairly tricky. Okay, finishing this off, we could, instead of writing 3 integrals, I think just write 2. I think 2 is probably the way to go here. Sadly, the purple one is going to stay, but you could simplify this, right? You could say it's from pi over 6 to 5 pi over 6, but this is 9/2 d theta. Easy antiderivative there. And then our second one, well, how can we condense this down? There's different limits of integration here. Oh, wait. Those slivers are the same size. Let's just double one of them. Let's just double the original one from 0 to pi over 6. 1/2 6 sine of theta squared d theta. Or you could even, now that there's the 2 there, get rid of those. And there we go. That will find your area. All right, the last problem is actually going to be a free response practice here. So what I'm going to have you do is go ahead and pause me and see what you can do with this. This is calculator active. Many of these do not require you to have done the other parts. For example, if you're stuck on part B, then skip to part C. If you're stuck on that, skip to part D, and so on and so forth. You do need a calculator for this one. I'm going to show this to you on Desmos, but I would suggest you use your graphing calculator since you can't use Desmos on the AP exam. And then as you get stuck, or if you finish it all, unpause and see how you did. Ready, set, go. All right, part A. Sketch the graph on the coordinate plane to the right. Use your calculator to help. I don't know what this graph looks like. We might be able to figure it out, and there are certain ways, certain methods, but I don't want to. I know we're only rotating from 0 to pi, so let's take a peek at that. This was our first one. It looks like I did pretty well on my graphs there. This was the second one. Here is the third one, though. Oh, it's wild. This one goes from 0 to 2 pi, though, so I wonder if this will accept pi. No, it will not. That was rude. Okay, so let's just plug in pi here. I didn't bother hooking up my keyboard, and now you can see that apparently I don't know where the pi symbol is, so that's awkward. Stop that. There it is. Hey. Okay. It looks weird. It goes like this, and then whoop, kind of spins around there. I don't know, maybe it's like a coat hanger, just the top part of a coat hanger, but on its side. I don't know. Oh, wait, where does it intersect the x-axis? Looks like at approximately 2, 2, and 2. So all sides, it looks like it goes through at 2. So 2, 2, and 2. Kind of curls, and it curled in, and then bounced back out. And I think it probably went out further that way. I don't know. Whatever. Doesn't matter. Great. There is my weird wonky graph. Nifty. Find the area bounded by the curve in the x-axis. Don't forget to show a beginning and an end. Oh, guys, this is so nice. There's only one graph. Woo! Just between the curve and the x-axis. Well, if you think about drawing radii from here, we just go from 0 to pi and we use our area formula. 0 to pi, 1/2, 2 plus sine of 2 theta squared d theta. Nice. They did say find the area, though, so you will need to use your graphing calculator to actually come up with the area for this one. So make sure you try that out. You could multiply it all out, but that sounds terrible. I'm just going to, again, stick with Desmos just because I think it's a little bit more clear. You should use your calculator, though. So here we go. It's the integral from 0 to pi of 1/2, 2 plus sine of 2 theta squared d theta. Don't forget you can use x as well. 7.068. So approximately 7.068. Go us. Does that make sense? Well, let's see. I meant to pull up the Desmos graph. This kind of looks like a circle here. I know it's probably not a circle, and maybe it's even a circle with like a radius of, I don't know, 1 give or take. So pi r squared, 3.14 plus another section. I don't know. It's in the ballpark. Nothing bad. All right. Find the angle theta that corresponds to the point on the curve with an x-coordinate of -1. Oh, this one's getting wild here. So an x-coordinate of -1. We can certainly tell there's a point there, right? This is -1. It seems like it's +1. But we can't just say it's +1. We looked at the graph, right? We need to actually show the calculations on this. And that reminds me, on part B, it says, please show a beginning and an end. If you just write 7.068, you don't receive full points. They always want to see a setup and an answer. No bald answers. All right, so angle theta. X-coordinates. What do I know about x-coordinates? I think I know that the x is always equal to r times the cosine of theta, isn't it? And we know they want the x-coordinate to be -1. But then I'm at a bit of a crossroads here because, or an impasse rather, because I have an equation with two variables, r and theta. So what do I do from here? Oh, wait, we know what r is in this case. Isn't r this function up above? So we can go further and we can say -1 equals, I'm going to put the times cosine of theta at the end so I don't forget about it. And this was 2 plus sine of 2 theta. Nice. Now we're in business. Except, wait, how do we solve this? This looks really challenging. Oh, this problem's calculator active. So remember, to solve a calculator active problem, you don't need to show your process. This is the setup. This is my answer. In order to solve this, let's just use our calculator. In particular, don't forget, if you have an equation that's tough to solve, we don't set each of the factors on the right equal to -1. You can only do that when it's equal to 0. Instead, we graph each side of the equation and determine their intersection points. Now when I'm graphing, I'm not graphing in polar here, right? We're looking for x-coordinates. I'm going to graph y equals this and y equals this, and I'm going to use x instead. So let's see what this looks like. So I have y, we're going to temporarily turn you off. We have y equals -1. Then we also have y equals 2 plus sine of 2x. I know it's kind of weird. And then cosine of x. Isn't that what we're looking here? Yeah, very nice. Okay, and we're looking for where we have an x-coordinate of -1. Well, there's all sorts of these guys over here, huh? This is pretty wild, right? Look at all these pieces. Well, how do we choose which one is the correct one? There are a few ways to think about this, but let's just bring some logic in. Let's look at the original graph again. Okay, on this original graph over here, we're looking at -1, comma something. And we're looking for a rotation of theta, aren't we? That's going to bring us over here. So think about rotations of theta, right? This is pi over 2. This is pi. Pi is 3.14, isn't it? And we know that theta has to be between 0 and 3.14. So if we look at my green graph down here and we look at these intersections, we want the answer, because x is standing in for theta, isn't it, right here? We're looking for an answer that's between 0 and 3.14. And I think it's got to be 2.63, doesn't it? That's too big. This one's too small, so 2.63. And this is kind of the downside of Desmos right here is that doesn't go far enough in terms of decimal places. So hopefully you're using a graphing calculator that does go further. I'm actually not sure how to force Desmos to go further than that, but 2.63 something here. So 2.63 something radians. So we can actually check this answer. It actually took me a little bit of playing around to figure out how to check this answer, so bear with me and I'll try to talk you through the process. So what I did here is I created a point at the spot where I was pretty sure it was supposed to be, and this is one really easy way to check it. I took our 2.63 and I plugged it into our formula. And remember our formula to find a coordinate in, I should probably pull this over so you can see the whole thing. Our formula to convert r and theta into x and y coordinates is you do r times cosine of theta and then r times the sine of theta. So I plugged those in first and I was like, hey, I think this looks pretty good. This looks like it's in the right spot. And if I click on it, you'll even see it's approximately -1. That's because I rounded 2.63 and we got there. But then I figured I could also do something cool. And so I said, well, let's only draw this graph from 0 to pi, or I guess I did 2 pi in this case. And I said, well, if we rotate this graph, right, here is 1 radian, right, where pi radians 3.14 is right about here, right? That's halfway around. So I said we can draw this graph, and this is essentially the c value is the theta rotation. And so if I stop it at 2.63-ish, it should be right on the point we're interested in, and it is. So that is pretty cool. We have now found the angle theta that corresponds to the point on the curve with an x-coordinate of -1. Alrighty. Part D. Find the value of dr d theta at the instant when theta equals 5 pi over 7. What does that tell you about the curve? This is a calculator active question. We should be doing pretty much all of this on our calculator. So we have r equals, right, and then 2 plus sine of 2 theta. And then technically you would do d theta of each side, which you can absolutely do by hand, but I'm not going to because we don't have to. Maybe I'll show you after this and you can skim over it if you want. But I'm just going to skip straight to taking dr d theta evaluated at theta of 5 pi over 7, and I'm going to give an answer. Right? There's no reason to do any more work. This is calculator active. And I think I can do this on my computer, so let's see how this goes. I'm going to go ahead and get rid of all this. We're going to set the graph back to be between 0 and pi, and we're going to say dr, that's probably not, it's not going to like that. I wonder if I can say r of theta. That looks good. And then I wonder if I can say r prime of, and then it was 5 pi over 7, wasn't it? And we can. How exciting. So Desmos worked just fine. On your calculators, you would be using the derivative function, right? On the 84, you'd be doing math and derivative and plugging this in. If you're on the Inspire, you'd be going to calculus, derivative at a point, plugging in 5 pi over 7. So we got negative 0.445. Negative 0.445. What does that tell you about r? Well, this is saying as theta changes, or as theta is changing, right when theta is 5 pi over 7, r is changing by negative 0.445. And if you wanted to add in units, we could say, nope, that's not right. Did they even give us radius units? Yeah, r is measured in meters, so meters per radian. And I always like to put it over 1. So what this is saying is every 1 radian we increase, right, we move to counterclockwise to the left, our radius is shrinking by 0.445 meters. And we can even see that over here. It's a really bummer that I kind of erased everything. But as we're going over here, we're talking about 5 pi over 7. Let me see if I can quickly whip up what I did before. I did like 2x plus b. We're going to add a slider here, turn this off. We're going to go from 0 to b. We're going to set b to go from 0 to pi. And we'll have it step by, oh, let's just have it step by pi over 7s, I guess. And yeah, I think if we go then a bunch of steps. So here's 0 pi over 7, 1 pi over 7, 2 pi over 7, 3, 4. Here's 5 pi over 7, give or take. But let's think about the journey that our graph has made here. At the beginning, it is a radius of 2, and then r clearly is bigger. This is definitely bigger than 2, right, for sure. And then as we eventually get up here, we're now back to 2, aren't we, right about here? So we started at 2, r increased, so dr d theta would be positive, but then r starts to decrease, so dr d theta is negative. Okay, as we continue over, this is 1, 2, 3, 4. Here's 5 pi over 7. Look at this radius right here. That's a really, really small radius. So from 2 down to maybe 1, but our radius is still decreasing. And then as I continue out, look over here. This radius, this is probably the smallest the radius gets. And then if they had asked us about 6 pi over 7, I bet 6 pi over 7 would be positive. Let's double check. It is, because what happened at 6 pi over 7 is in the previous section, the radius is now growing. And at 7 pi over 7, the radius is bigger again. Dr d theta is just telling us if the radius is increasing or decreasing. Negative means at a rotation, always at for derivatives, at a rotation of 5 pi over 7, the radius is decreasing at a rate of 0.445 meters per radian. I did promise you the derivative by hand, so if you wanted to see that, 2 becomes 0, sine becomes cosine, 2 theta times the derivative of the inside, which is 2. And then you could just find r prime of 5 pi over 7. You'd use a calculator here, and you'd get some sort of decimal, right? So you can do it that way. Alrighty, last problem for the day. Particle is traveling along the polar curve given by the same polar curve that we've seen, so that its position is time t, vectors, is such that d theta dt equals 3. Find the value of dx dt at the instant that theta equals pi over 6 and interpret the meaning of your answer in context of the problem. Holy Toledo. There is a lot going on here, isn't there? Okay, let's see. What do we want to do first? So we know d theta dt. I'm seeing d dt here, right? So why don't we go ahead and at least take the derivative? Let's see, they want the value of dx dt, don't they? So why don't we find an equation that has both x and theta in it? And think about taking the derivative with respect to t. So what equation do we know that relates x to theta? Oh yeah, x equals r times the cosine of theta. X is the output. We have 2 inputs though, but I think we can be better. I think we could probably say that x is equal to, instead of r, 2 plus sine of 2 theta times cosine of theta. X and theta now, right? They want the value of dx dt at pi over 6. Okay, well, let's take the derivative of this. I think before I take this derivative, we'll do one more, and we'll distribute the cosine of theta. So 2 cosine of theta plus sine of 2 theta times cosine of theta. I'm trying to decide if that's going to be easier or not, but I'm going to go with it, whatever. So dx dt. So I took the derivative of x ddt of that side, and we'll show this work. I'm also going to take the derivative of this side. 2 cosine of theta, well, the derivative of cosine is negative sine, so it becomes negative 2 sine of theta times the derivative of the inside, which is d theta dt. All right, the next one, I'm going to go ahead and put in big brackets because we need to use the product rule here, right? And I will group this so we can see the product rule in action. The derivative of sine of 2 theta we saw before is cosine of 2 theta times, and this is not going to be nearly enough room, times 2, so the derivative of the inside, but not just times 2, it's times 2 d theta dt. Oof. And then times cosine of theta. I should do that in blue, sorry. Nifty, but that's only half the product rule because we kept that the same. So then we need to add on the original same function, which is sine of 2 theta. And we need to do the derivative of cosine, which is negative sine of theta. What a wild derivative here, isn't it? Okay, now what? Well, now we need to evaluate this at a theta of pi over 6. We are also given that d theta dt is 3. So we're going to find dx dt evaluated when theta is pi over 6. So what does that look like? Negative 2, let's do some math in our head. Sine of pi over 6 is 1/2. D theta dt they gave us is 3. I'm going to drop the parentheses now that I know what's going on. This is going to become cosine of, and I'll show this, cosine of 2 times pi over 6, which is really cosine of pi over 3, but, sorry, I skipped that step. Pi over 6, which is cosine of pi over 3. We'll get back there. D theta dt, cosine of pi over 6. And then sine of 2 times pi over 6. And really, because there's a minus there, we should probably change this to a minus, times the sine of pi over 6. And knowing AP exams as you do, hopefully you'd realize you can stop right there. However, we might as well clean this up. Cancel, negative 3. This becomes 3. Cosine of pi over 3 is 1/2. 1/2 cancels the 2. And so we end up with plus 3 times square root of 3 over 2. That's cosine of pi over 6, I think. This becomes pi over 3, so this becomes minus root 3 over 2. And sine of pi over 6 is 1/2. I really don't want to clean that up any further. However, they did ask us to interpret the meaning of our answer. So let's maybe just find a decimal equivalent here, unless you guys want to do any more math, which I really don't. So hopefully you could have just plugged all this into your calculator. Let's figure out what's happening in terms of decimals, interpret this, and call it good for the day. So I'll get rid of all these guys. Let's keep that. Might need that again. So negative 3 plus 3 square roots of 3 over 2 minus the square root of 3 over 4, isn't it? Over 4. No, go down there. There we go. 4. Awesome. Negative 0.834. Okay. Negative, I should probably put that, negative 0.834. So what's happening here? Well, x is changing as time progresses at pi over 6, a rotation of pi over 6, and we can even see that rotation of pi over 6. Let's go ahead and just change the step over here. Let's say that it's going from 0 to pi, and we'll have it go by pi over 6's. Why not? So the very first one here is 0. Here is pi over 6. Let's estimate that x-coordinate right there. That x-coordinate looks like it's about 2.5, right? 2.5, give or take. Okay, well, originally the x-coordinate isn't even there. 2.5, where is it now? So this is at 2.5, and then at a rotation, this is pi over 6. At 2 pi over 6, the x-coordinate is now at 1.5. Did the x-coordinate increase or decrease? Well, I'm pretty sure it decreased, didn't it? And so this negative value is telling us that the x-coordinate exactly at pi over 6 is decreasing at a speed, I guess, and we could put dx, which is the x-coordinate, right, whatever the units are, so x units per time. So every 1 time unit, the x-coordinate is decreasing at 0.834. Okay, just to make sure we're comfortable with that, let's look at 3 pi over 6. So we were at 1.5 at 3 pi over 6. Now the x-coordinate is at 0, so we're still decreasing. X is decreasing, decreasing, decreasing. I think you can actually argue the only time the x-coordinate increases is in this little stretch right here. It starts at 2, and then the x-coordinate eventually gets over to 2.5. So I bet if I had evaluated this at pi over 12, then pi over 12 would have given us a positive dx dt. So thank you for hanging out and doing some tough math. This is not, I think, representative of the difficulty level of a regular AP free response. In fact, this is probably harder. Please don't forget what we talked about in terms of the 2 different types of areas. And I'm excited to have you back next class for some additional area and polar practice.